In the last video, we looked at acid dissociation equilibria in Ka in detail. In this video, we're going to turn our attention to base association equilibria, the major reactions of Bronsted bases in water, and look especially at Kb, the equilibrium constant for base association. We're also going to discuss the strengths of acids and bases in a little more detail. So let's return to the self-ionization of water one more time. Water can react with itself to form H3O plus and OH-, and in this reaction, one molecule of water acts like a base, and one molecule of water acts like an acid. We get the transfer of a proton from one of the water molecules to the other, and the products are thus H3O plus, that's the conjugate acid of water, and OH-, which is the conjugate base of water. To write reactions of Bronsted bases, we replace the basic water with a generic base B. The acidic water is still there, and the products are then the conjugate acid of the base, Hb plus, and hydroxide. The equilibrium constant for this process is called Kb, the base association constant. And it's called an association because the base is associating with a proton to form the product conjugate acid. Kb has the same form as all equilibrium constants, products over reactants, and in this particular case we have the concentration of hydroxide, OH-, times the concentration of the conjugate acid, Hb plus, divided by the concentration of the base, B. No need for any exponents here since all of the stoichiometric coefficients are 1. As we saw for Ka, a large value of Kb indicates that products are favored, and in this case that indicates that the concentrations of Hb plus and OH- will be large at equilibrium. In other words, the base will be associated to a large degree. A small Kb value, much less than 1, indicates that the base is mostly unassociated B, and thus that the reactants are favored. Because hydroxide appears in this equilibrium expression, in most cases we'll be solving for OH- concentration when we're solving equilibrium problems involving base association. So the question arises, how do we get from an equilibrium hydroxide concentration back to, say, a concentration of H3O plus or a pH value? Remember that the self-ionization of water is always at equilibrium in aqueous solutions. That means that the equilibrium expression for that reaction, H3O plus concentration times the OH- concentration, is always equal to Kw, which at 25 degrees C is 1 times 10 to the negative 14. If we apply the p operator to both sides of this, we get that pH plus pOH is equal to 14. So if, for example, we have the concentration of hydroxide from solving an equilibrium problem with, say, a weak base in water, then to find the pH that corresponds to this hydroxide concentration, we need only take the negative base 10 logarithm of that. That's equal to the pOH, and then we can use the idea that the pH is equal to 14 minus the pOH to calculate the equilibrium pH. All of this relies on the fact that because we're at equilibrium, we can state with certainty that the equilibrium expression must be equal to Kw, and pH plus pOH must be equal to pKw, or 14. So we can calculate the concentration of hydroxide from the concentration of H3O plus, and more important for basic equilibria, vice versa. We can calculate the concentration of H3O plus and pH from the concentration of hydroxide. The other thing that this shows us is that hydroxide and hydronium concentrations act like a seesaw. When a base raises the concentration of hydroxide, then the concentration of hydronium must decrease such that the equilibrium expression, the product of these two, is still equal to 1 times 10 to the negative 14. When one concentration goes up, the other must go down. Now that we've seen the form of the equilibrium expression for Kb, for base association, we can make an interesting observation about Ka and Kb for conjugate pairs. Remember, a conjugate pair consists of an acid and its conjugate base, which is missing one proton relative to the acid, something like Ha and A-. So we've seen already that acid dissociation and base association equilibria can be imagined by replacing water in water's self-ionization equilibrium. The self-ionization of water is here at the top, and if we replace the acidic water with Ha, we get an acid dissociation equilibrium right here, and if we replace the basic water with A-, we get a base association equilibrium. What are the equilibrium expressions for each of these reactions? Well, for the self-ionization of water, it's pretty straightforward. Kw is equal to the product of H3O plus concentration and OH minus concentration. We've seen this several times by now. Ka for the acid dissociation is equal to the product of H3O plus concentration, A minus concentration, these are the two products, divided by the concentration of HA, all at equilibrium. And for this base association process, we can write that Kb is equal to products over reactants as well, which in this case is the concentration of hydroxide times the concentration of the conjugate acid, which, since we're dealing with HA and A minus is the base, the conjugate acid is HA, divided by the concentration of the reactant, which in this case is the original base, A minus. What happens when we add the acidic equilibrium for HA to the basic equilibrium for its conjugate, A minus? Well, when we add the two equations, watch what happens. We have A minus on the product side of the acid dissociation and the reactant side of the base association. And we have HA on the reactant side of the acid dissociation and the product side of the base association. So the only things that survive when we add these two reactions together are two molecules of water on the reactant side, and on the product side, H3O plus and OH minus. This is just the self-ionization reaction of water. Two molecules of water forming one molecule of H3O plus and one molecule of hydroxide. And as we've seen before, if we want to calculate the K for this reaction, since we added the acid dissociation and the base association, we have to multiply Ka and Kb. And in fact, if we do multiply Ka and Kb, what we find is that A minus cancels out in the numerator of AD and the denominator of the Ba equilibrium expression, and HA cancels out as well. It's in the numerator of the Ba equilibrium expression and the denominator of the AD equilibrium expression, such that the only thing we're left with is the concentration of hydronium times the concentration of hydroxide, which is equal to Kw. Notice that Ka and Kb are acting like the concentrations of hydronium and hydroxide on the seesaw that we saw before. What this little derivation is telling us is just the same thing we saw for hydronium and hydroxide. When Ka is large, when the acid HA is a strong acid, then Kb for the conjugate base must be small. And vice versa. When Kb is large, that is when A minus is a very strong base, well then Ka must be a very weak acid. There's sort of a conjugate seesaw going on here. That's because the product of Ka and Kb must equal Kw based on this relatively straightforward derivation. Another way you may see this involves applying the p operator to both sides. When we do that, we get pKa plus pKb, because of the properties of logarithms, is equal to pKw, which is equal to 14. This is a pretty remarkable result, and the conceptual idea behind this conjugate seesaw is really important to understand. When HA is a strong acid, that means A minus is necessarily a weak base, and when HA is a weak acid, that means that A minus is necessarily a strong base. So large Ka then is associated with strong acids, which are essentially completely dissociated in water at equilibrium. We've seen this before. A good cutoff is a pKa less than 3 corresponds to a strong acid. With a pKa that low, the products are going to be heavily favored, and so we'll have essentially complete dissociation at equilibrium. Weak acids have relatively low pKa values and have a pKa, for example, above 3. And these exhibit a small to negligible amount of dissociation in water at equilibrium. Similar ideas apply for strong and weak bases. Strong bases have large Kb values, which correspond to low pKb values, something like pKb less than 3. Weak bases have relatively low Kb values, relatively high pKb values, and exhibit a small to negligible amount of association in water at equilibrium. These are mostly the base, just like weak acids are mostly HA. Strong acids, on the other hand, dissociate to form mostly H3O plus and A minus, and strong bases associate to form mostly Hb plus and OH minus. And for strong acids and bases, these are essentially complete so that we can basically replace the concentration of the acid with H3O plus and the concentration of the base with OH minus. The strong acids and bases are actually relatively limited. There's a small list of strong acids and bases. The hydrohalic acids are very common strong acids, HCl, HBr, HI. You'll notice that HF is missing from this list. HF is a weak acid, not a strong acid. Other important examples include chloric acid, HClO3, perchloric, which is HClO4, nitric, which is HNO3, and sulfuric, H2SO4. It's worth committing these strong acids to memory or writing them down on your crib sheet. Strong bases are the salts of hydroxide, especially of the group 1 metal cations. Lithium hydroxide, sodium hydroxide, and potassium hydroxide are the most common examples, but rubidium and cesium hydroxide also fit into this category. The heavy group 2 metal hydroxides are also strong bases. Calcium hydroxide, strontium hydroxide, and barium hydroxide are 3 examples. And remember that the conjugates of these are weak acids and bases. In other words, for example, Cl minus is a weak base, Br minus is a weak base, I minus is a weak base, NO3 minus is a weak base. These are all weak bases. Why is that? Simply because the product of Ka for these strong acids and Kb for the conjugate base must be equal to 10 to the negative 14. And so if Ka is very, very large, as it is for these, then Kb must be relatively small, so the corresponding conjugate bases must be weak.